I'll be explaining the theory behind freefall. And so when a person initially jumps out of the plane, they have a force of weight acting towards the ground, and there'll be little to no drag initially. This causes a large resultant force acting downwards, in which the person will begin to accelerate at 9.81 meters per second squared, and their velocity will begin to increase. Since their velocity is increasing when they fall down, there'll be a drag. And this is because the drag force is actually due to the kinetic energy of the air molecules hitting the object. So if the speed increases, the kinetic energy of air molecules squares. And this gives us the equation that drag is directly proportional to velocity squared. And as the velocity increases, drag increases until drag is equal to the weight. Once drag is equal to weight, since they act in opposite directions, they'll cancel one another out, and the resultant force will be zero. Once the resultant force is zero, the skydiver will be traveling at a constant speed, also known as terminal velocity, and this describes Newton's first law. When the skydiver is traveling at terminal velocity, during some point of time, the skydiver would like to stop or decelerate so they can land safely, in which they'll deploy their parachute. When they deploy the parachute is structured in a way that has a large surface area, and it is not very aerodynamic due to its curvature. And this causes more air molecules to hit the parachute. And as mentioned before, that drag is the kinetic energy of air molecules hitting an object. This means that drag will increase, or the K value for our drag equation will increase. This causes a larger drag force, which will be larger than a weight, so resultant force will be now acting upwards in the opposite direction, causing the skydiver to decelerate. As the skydiver decelerates, their speed will decrease, and according to the drag equation, if speed is decreasing, drag also decreases. So drag will decrease until it's equal to weight once again, and then resultant force is equal to zero, and the person will be traveling at terminal velocity when they will be able to land.
For this experiment, you need to use a data logger that is connected to a light gate and a double interrupt card that will pass through the light gate. First, to measure the time taken of the blocks to go through, you need to measure the width of the blocks and calculate the midpoint. Then drop the double interrupt card through the light gate, make sure that the midpoint is aligned with the certain height that you want to drop it from. When the card is dropped, you'll get two readings on the data logger. The first reading will be the time taken for the first block to pass through, and the second reading will be the time taken for the second block to pass through. Repeat this experiment at least 6 times, making sure to drop it from the same height.
You should get 2 times. The first one is the first block from the data logger, and the second time is the time taken for the second block to pass through the light gate. And in order to find initial velocity, this would be the width of the first block on the double interrupt card divided by your first mean time, which we've shown in the graph. And to get your final velocity, it will be the width of the second block divided by the second mean time. Since you got both final and initial velocity, and our distance, our S value, will be equal to the middle distance between the two blocks. And since you got velocity, initial velocity, and distance, you can use Suvac equations to find the acceleration. Yeah, for the alternative experiment for measuring acceleration, you got the same apparatus and same setup, and you also again measure the width of the black box and find the midpoint. You'll align the midpoint with roughly 10 centimeters on the ruler, and you'll drop it at least 3 times to get a time reading, and you only should use the first time reading that you get on the data logger. And each trial you should increase by 10 centimeters, and then repeat experiment 6 times, and then you're done. Yeah. This is what your data table should look like. And in order to find velocity, you got to find the width of the block, which I got down as 4 centimeters, and do your width of the block divided by the mean time for each distance interval. And this will give you velocity, and you can square the velocity. The reason why we've got to square the velocity is because using one of the Suvat equations, v squared equals to u squared plus 2as. Since our initial velocity will be 0, so it will be v squared equals to 0 squared plus 2as, and we'll be dividing it by, and to find acceleration, you do v squared is equal to s is equal to 2a, and this is what we have in our graph down below, where I got the y-axis as velocity squared and the x-axis as distance dropped. And you should get a linear line, and that will give you 2a. And in order to find the acceleration, you find the gradient of the line by taking 2 points and find the gradient, and then dividing that by 2, and that should give you the acceleration. I also drew the graph myself with velocity squared as the y-axis and distance dropped as the x-axis. I got my best line of fit, which where 2a was equal to 20.75 and a would be equal to 10.375 meters per second squared. However, we know that acceleration is actually 9.81 meters per second squared, so I can calculate the uncertainty in my result, which would be 9.81 subtracted by 10.5 divided by 9. And this gave me roughly 5.81%. This is my uncertainty. This 5.4% of uncertainty or error can occur for a few errors I made during our practical experiment. One of them could be a parallax error, and that is when you don't really line up the midpoint and the midpoint of the double interrupt card and the ruler correctly or well, so your eyes aren't really in line with it, so you can't really find the correct measurement. And also, we found that when doing the experiment, when actually dropping the double interrupt card, a lot of times the double interrupt card will will not fall down completely vertically, or it might accidentally hit the side of the light gate, causing a change in time reading. And so these slight things can cause this 5.4% error. However, with this 5%, since it's a relatively small percent of error, it shows that our experiment is accurate but not very precise. So yeah.
Dude, this is so hard, bro. My hands got.